Next, we look at the architecture deep dive. For this, we're going to focus on, I guess, building up our knowledge of the microservices that are being invoked under the covers, the underlying infrastructure. How does that look? How do the nodes look? How the data moves throughout the system, as well as the various ingest and egress options. So out of the box, we provide these pre-built microservices, like what I mentioned at the start, for all of the data capture and query of the solution. So that's built into everything that you've seen so far. So data starts at one end, either streaming data or batch data, both are fine. And the entry point typically is a layer like reliable transport. That looks after high availability of data across multiple nodes. And then publishes down into the stream processor. The stream processor is essentially what you see within the pipeline builder. So this is where you can like apply the streaming analytics that we created, or the machine learning components. We can do aggregations of data. We can take a raw stream of data and transform it into a new table, branch into multiple tables if we need, things like that. Normalization, all of that takes place within the stream processor. And again, stream processor can be used to import the batch data or import streaming data into the system. Then the stream processor will publish that data set to two other microservice components. The first is the storage manager. Storage manager is essentially what looks after the write down of data into the server. So let's say it's every 10 minutes, it's going to move data from that RDB location into the intraday. At the end of every day, it's going to move it into the historical database. And then at a configurable point in time, it's going to start moving data from those fast storage devices into the slower form of storage, or the archive. So the storage manager looks after that. It's what allows you to keep an overall very low memory profile within the system, which is great when you're deploying on the cloud, because cloud boxes, the more RAM that you essentially license for, will drive up the cost of your cloud infrastructure. Then the data access layer. This is the RDB, IDB, HDB. So most recent data, slightly older data, and then everything else is stored in the database. This is essentially where your queries are run. So if you're a user that's connecting into the system to query that data, you're essentially interacting through the gateway component, and the gateway is going to route your query to the correct assembly. And within that assembly, you're going to have the databases. You can even query across multiple databases if you like, and then the aggregator will join that data and send it back. Now, when we say that I guess that our architecture components are pre-built, off the shelf, ready to go, it doesn't limit you in terms of what you can build on top of this application. Again, it is like a development framework. The system will allow you to build your own custom functionality on front or on top. So for example, maybe you want to build some like alert logic into the pipelines. Well, you can simply inject using the mapping node that I showed earlier, data directly into the stream processor. You can inject that using either Python or Q, for example, or likewise in the data access. You can start to define your own custom functions that can be called by the dashboards or called by your other third-party applications. So slowly but surely, you're then starting to build up your own package of code on top of the foundational components which are provided by KX. Each of these components are hardened, so they're tested, they're bulletproof, provided by KX to the best of KX's ability. So that's I guess, a very quick summary view of those microservices. We'll go and touch upon each in a little bit more detail shortly. This is the infrastructure design. So I mentioned earlier, we typically deploy in a minimum of 3 nodes. So that's 3 nodes split across 3 separate availability zones. And within each availability zone, you will have an RT, so that's the reliable transport, the stream processor, RT south again, and then the data access process. Then you have the storage manager. The storage manager will only run and be active on any one node at a time. However, if a storage manager fails for a reason on a specific availability zone, maybe even the zone crashes, then that storage manager will start up within one of the other availability zones. In terms of storage, we mentioned earlier that KX use a distributed file system like EFS or Rucksafe, for example. So the storage manager is essentially writing down one copy of data at a time into that storage structure. And we're using the replication within the file system itself to replicate across to multiple, replicate that storage to other zones as well. So 3 nodes is our minimum configuration for this application. You can scale both horizontally and vertically. So let's say you have more and more applications getting added on, but your data volumes don't change. Well, you can add more and more compute pods for your data access processes, for example, and scale those further without having to increase the RAM, for example, of the node, without having to increase the size of the other pods within the system. However, if you are actually increasing the amount of data you want to capture, then that's probably where you're going to start going up within your RAM sizes, because you're always holding a certain amount of data in memory. So this is just a brief explanation of each of those microservices. This is, again, another diagram which kind of goes into a bit more detail than the microservice diagram I showed earlier. It was much more simplistic than this. So, well, let's just take this one step at a time. We have the concept of an assembly. Within an assembly, you can have your streaming processor. So essentially, you can have multiple pipelines within that single assembly. And then each assembly will have its own storage manager and its own data access layer. Okay, so that means that every assembly will essentially have a database. A database is the same as an assembly in the context of what you've seen earlier through the UI. And then, as you've seen earlier through the UI, we were creating multiple pipelines publishing into that one database. The system also supports obviously having then multiple assemblies as well within it, which therefore means you have multiple storage managers writing down into the underlying, I guess, storage layers. So upstream, we have our data ingest point. So let's say it's Kafka, and that's being published directly into our stream processor. The stream processor is making that data available into the storage manager and also publishing it through to the data access layer. If a user logs in and wants to spin up a query pad or a scratch pad, they can do so. That'll essentially spin up another data access layer. They'll connect to a secondary a data access layer or a sandbox environment. And again, earlier when we discussed about controlling some of those settings relating to the access to data for your applications versus access of data to the sandbox users, that's essentially where you're stating what's the maximum number of replicas you can have here. So everything you're doing through the UI itself is what's orchestrating the underlying compute, and is doing that through those coordinators. So as you add a new node into your pipeline, the SP coordinator is spinning up the correct functions and compute instances and connecting the processes together and so on under the covers for you. So looks a little bit complex, but it really isn't. Then going and diving into each component. So the storage manager, as I mentioned earlier, it looks after your, or it ensures data is written into the database in a highly resilient manner. It ensures that data consistency is always maintained. And it also means that as data is being written in and somebody's querying, you will never have any errors. So it uses this double buffered write down strategy. So essentially what happens here is the storage manager is receiving a stream of data from the stream processor, like what we mentioned. And within, on a timer basis, controlled through the UI, it's then doing a write down into that intraday database location, which is just another storage location on disk. Then at the end of day, it's moving that data from that intraday location into a date partition, which is available on disk. Then the database manager process, as part of that storage manager, will slowly and surely migrate the data across the tiers on a configured time. So that could be every month, move data from one storage option to another, and every 6 months move it into the final location, or perhaps even delete it. So the database migrator looks after all of that. Then you have the data access layer. Again, this is essentially just giving one seamless layer for if you want to access the real-time data or the intraday data or the historical data. So simply inject your function into those processes and you'll be able to query that data. And data is always queryable and it will always be consistent no matter who is querying. So if you have multiple users accessing the data at the exact same time, they will always have the same consistent view of that underlying data set. Those users that are accessing will typically hit the gateway. The gateway will essentially route the request through the resource coordinators. So the resource coordinators are tracking, how busy are the underlying data access components, which again are the RDB, IDB, and HDB, and it's directing to the most available one at any point in time. The results are then sent back to an aggregator, which is then published back to the client. So that resource coordinator may send a query to an RDB and an IDB within database or assembly 1, and an RDB and an IDB within a different assembly or a different database, depending on what your application is actually doing. So all of that ends up being sent back to the aggregator, which will then send it back to the deploy. And then the application is able to decide how many of these aggregators do we need in order to meet the various loads that are required by the downstream applications themselves. Obviously, there's much more to this than just all of the components that KX provide. You also have a lot of integration then with the cloud services themselves. So let's say you could be tiering the data with Microsoft Azure Blob Storage, for example. Or you could be publishing alerts out to Azure Event Hub. Again, this is an Azure example, and all of the other cloud providers have the same. There's other third-party tools for managing this on-prem as well. You're interacting with load balancers that are available on the cloud. You're connecting to the likes of Azure Active Directory. That would be through another third-party tool, which is Keycloak. So there is a lot that's happening and going on here as well that's actually not related to the flow of the data set itself. So just keep that in mind. The system actually removes you from a lot of that complexity. But when you go into, let's say, a custom managed deployment, you have a lot of configuration options in that area too through the various YAML files or Terraform deployment scripts. Okay, in terms of reference cluster sizes, this is version 1.5 and it will change in the future version 1.6, which is coming out at the end of this month, which actually will give it even more even better results. So within a 128 gig node, KX are essentially can ingest anywhere between 20 and 750 gigs of data per day. So that's around 2 billion records with 50 columns, for example. So that's quite a lot of data. Of course, we have 3 of those nodes for that resiliency through the reliable transport layer. So our total cluster size is roughly about 384 gigs of RAM. So quite small for, let's say, ingesting a very large data set of 750 gigs. So I do think that's quite impressive. Next, we move on to our data ingest and egress options. Again, at the center of this, you have the out-of-the-box components for your data capture that we've already discussed, as well as the out-of-the-box built-in features to that app. So the monitoring, security, machine learning libraries, high availability, web-based UI, Keycloak, etc. But what are the other connectors and so on that actually sit around this that allow you to ingest and connect to receive data? So the raw data sources that we have out of the box is essentially being able to connect to a Kafka, a message bus, MQTT, hitting a HTTP endpoint. So let's say it's, I don't know, BitMEX is an example, crypto, you can hit their HTTP endpoint and pull data in on a daily basis, for example. You can import files, be it CSVs, JSONs, or other formats. You can query Postgres databases. You can query an SQL server. You can generate your own fabricated data if you're just doing ad hoc sort of development. And then we connect to custom sources as well. So you can leverage the C SDK, for example, or the Java SDK and publish into that reliable transport stream if you like. You can also publish through Python. So that's using our PyKX library. When it comes to data queries, you can interrogate the data using Q. So that's, again, the programming language built into the KDB database itself. Or you can use SQL and Python. Or you can leverage the Get Data API. And again, you can then, using any of those, you can build your own custom APIs and connect to those as well. So that allows you to define other endpoints that isn't just to get data. It could be something like get latest sensor values, and then the application downstream can consume those. And then downstream, we have publishing to Kafka, we have Power BI and Tableau integration. You can connect your Jupyter notebooks. You can connect any applications through REST if you wish. There's also a Java SDK. So if you have, I think a lot of Subcon's applications today are Java based. So you can connect those in to consume data. And then there's also the dashboard builder that we've shown through this, which has that native integration as well.